Hello, let us start this lesson with this remark. The nth order Taylor polynomial for f about a is sometimes called the nth degree Taylor polynomial. But I want to draw your attention to this fact, but its degree will be actually less than n if the nth order derivative at a turns out to be 0. This becomes more clear in the coming example. That's why I always prefer to talk about the nth order Taylor polynomial rather than the nth degree Taylor polynomial. Okay, now let us solve the next example from the lecture notes. So this is example 9 in the lecture notes. To determine the nth order Maclaurin polynomial of the function f of x equals to sine x, write down the fourth order Maclaurin polynomial explicitly. What is the degree of this polynomial? Okay, so let me start with the formula of the Taylor polynomial. So this is the general formula. If I have a function f and a point a is given, I want to write the nth order Taylor polynomial of the function f about a. This is the general formula, but because in this problem they are talking about the Maclaurin polynomial, it means that a should be equal to 0. So if I plug a equal to 0 in this formula everywhere, I have 3 places to plug in here, here, and there, and then immediately I get this formula. But here, from pedagogical point of view, you will see that it is much easier to work with the extended version, not in the sigma form. And I will keep more terms than usual. You will see why shortly. So if I open up this, and because a is clear in this context, I will also suppress this 0. Then you will get this formula, this expansion. This is nothing except this formula, but I have expanded that. For example, if I put k equals to 0, x to power 0 is 1, k 0 factorial is 1, and the zeroth order of f, zeroth order derivative of it at 0 is just f of 0, and if I continue I will have this. But the only thing that I want to draw to your attention to is that I also kept the previous term. So this is the last term. When k becomes n, I will get this expression, but as you will see, it would be good for this problem at least that I write the previous term. So the previous term is like that. So now my duty is to calculate all these coefficients that you see here. Okay, so I have to do that. And that is not very hard here. You see, function f is sine x, so when I differentiate it, it becomes cosine. When I differentiate it again, it becomes minus sine. So the derivatives are either sine or cosine up to a minus sine. Okay, so let us take care of all these things in a table. So you already know that probably you have to divide your derivatives into even order and odd order, because some of them will be sine always, some of them will be cosine, as the calculation follows will show you immediately. Okay, so the function that we have, f of x, is sine x. Okay, so now if I differentiate it once, it becomes cosine x. Now if I differentiate it again, f double prime of x, the derivative of cosine turns out to be minus sine. If I differentiate this one again, then it becomes minus cosine. And if I differentiate it once more, the fourth order derivative, it becomes positive sine x, yes, because the derivative of cosine is minus sine. There is also a minus sine, so I will get sine x back. And I differentiate it once more, the fifth order derivative, it becomes plus cosine x. Okay, so it's already revealing a pattern. By the way, if you want to keep the consistency, you can write this as the zeroth order derivative, which is that one. So what you see here is that if this number is an even number, you are dealing with sine, and if this number is an odd number, you are dealing with cosine. The only problem that you have to be careful about is this alternating minus sign. So for example, let me just write one more of them. So if I go to f order 6, so what I have to do, I have to differentiate this one once more, so it becomes minus sine. And if I differentiate it for the 7th time, it becomes minus cosine. So you see that exactly the first one positive, negative, positive, negative, and then the same is true here, positive, negative, positive, negative. Okay, so it is not hard to see that if I continue the even column, so I would reach at some point, so let us say to 2k, 2k is an even number, at x, definitely it becomes related to sign. Yes, because all even ones include sign, so I would write a sign. So how can I take care of this alternating minus sign? You already have some experience about that, so you have to write minus to some appropriate power. Okay, so what is that appropriate power? So 2k, if 2k is 0, this means k is 0, and you should have positive. But if 2k is 2, 2k is 2, it means k is 1, you should have negative. So it seems that the appropriate power is just k. For example, let us test it for this case that it is 6. So if 2k is 6, then k is 3, and then minus 1 to power 3 becomes minus, and that is correct. You see that the sixth term is actually negative. So this is correct. And we can do similar thing here. So if I continue, for example, if I have f an odd number 2k plus 1, for example, then what happens? Either you can guess, or you can differentiate this once more, because this is the next order derivative. Yes, so it becomes minus 1 to power k to times cosine x. Or if you want to think through the pattern, it is very simple. For example, if 2k plus 1 is 1, it means k is 0, and you should have positive. But if 2k plus 1 is 3, it means k is 1, and it should be negative. So that's correct. Okay? But now my point is to calculate them at 0. So this means that it motivates me to replace x with 0. If I replace the even part if I replace x in the even column with 0, because sine of 0 is 0, I will get 0 all the time. But if I replace k with 0 here in this column, cosine of 0 is 1, and I get minus 1 to power k. Okay. So these are the calculations we have done so far. Okay, so this is the information we have so far. So this is our Maclaurin polynomial of order n, and we know that the even order derivatives at 0 are all 0, and the odd order derivatives at 0 are minus 1 to power k, so k is this number. So you see that we don't have any problems with even orders. So you see that this will be gone, this will be gone, this will be gone. But the problem here is that we don't know what n is, because n might be even or odd. If it is even, the last term will vanish. If n is odd, then this will survive, but this one will vanish. So somehow, hopefully, you are motivated to see that we have to actually separate the cases for even case and odd case. So let me consider n to be even here, and consider this scenario first. So if n is even, then it means that the last term is vanishing, okay? And of course, all the even terms are vanished. So this is gone, this is gone, this is gone, and the last one is gone. Okay, so we are supposed to write these terms. So what is f prime of 0? So according to the calculation we did, we can actually see immediately what happens. So what is f prime of 0? So when I say f prime, it means that 2k plus 1 is 1. So this means k is 0. So minus 1 to power 0 is 1. If this is 1, divided by 1 factorial remains 1. So I will get x. So this means that Pn of x in this case starts with an x. The next one is even, so it is gone. And what about this one? So this is the third order derivative. If I compare it here, it means that 2k plus 1 is 3, so this means that k is 1. And minus 1 to power 1 is negative, so this becomes negative divided by 3 factorial times x to the power 3. So the next term will be x to the power of 3 divided by 3 factorial. Okay, for example, if I want to write the next one of course is even and it is gone, but for the fifth one I will have f fifth order at 0, 5 factorial multiplied by x to the power 5, yes? And then if I compared 5 to 2k plus 1, then I realized that k should be 2 minus 1 to power 2 is positive. So the next one will be positive x to power 5 divided by 5 factorial. Okay, and now the next one, of course, will be negative. When I continue, because I am assuming that n is even, this one vanishes, but this one survives. But what is this expression? Okay, so I compare n minus 1 with 2k plus 1. So in principle, 2k plus 1 is n minus 1. So 2k becomes n minus 2, and then k becomes n minus 2 divided by 2. Okay, so this becomes minus 1 to power n minus 2 divided by 2. Okay, so this means that I can write plus minus 1 to the power of n minus 2 divided by 2, and then I have x to power n minus 1 divided by n minus 1 factorial. So this is for the case that n is even. Now we consider the case that n is odd. So what happens in this case? If n is odd, nothing changes except that this time, because n is odd, n minus 1 will be even, and this will vanish, but this will survive. So I don't need to recalculate anything again, so I have to consider the last term. So it means that Pn of x will be x minus x to the power of 3 divided by 3 factorial, x to power 5 divided by 5 factorial, minus, and we continue plus. And I will reach to which one is now n is odd, so I have to keep this one. So this means that 2k plus 1 is equal to n this time, so k becomes n minus 1 divided by 2. So this becomes minus 1 to the power of n minus 1 divided by 2, and this time I will have xn divided by n factorial. So depending on if n is even or odd, this will be my nth order Maclaurin polynomial of the function sine x. But the problem also demands to write the fourth order Maclaurin polynomial for sine x explicitly. So this means that I have to use this formula, because when I say n is 4, it means it is even. So if n is 4, so this means that I have to start from x and continue this pattern until I hit the last term. But here n is 4, so if I calculate that one, it becomes minus 1 to power 4 minus 2 divided by 2 is 1, and x to power 3 divided by 3 factorial, so it is this term. So this means that for this case, if I write P4 explicitly, it becomes x minus x to power 3 divided by 3 factorial. And that is what you get explicitly. And that is why I now hopefully you understand the importance of the remark that I started this lesson from, is that you see, even though I am looking at the fourth order Maclaurin polynomial, but the degree of the polynomial is indeed 3. Okay, so this is why I myself prefer to differentiate between degree and order, but I think in your course textbook there is no difference. Sometimes they are using it, but when I am talking about in my lectures, I will always consider order as the n and degree as the real degree of the polynomial when it's calculated. Okay, so I hope that this video was also useful for you. I will continue, of course, with more videos. Thank you very much, and be safe until next time.